Hi everyone, welcome to a 331 proof review video. In this video, I will be introducing how to use two of the most common and easy techniques you can use in 331 homeworks, proof by contradiction and proof by counterexample. Before we dive into these two techniques, I will first do a quick review of limits and asymptotic notations. Here is the overview of what we will cover in this first part. It includes defining function, limits, and relationships between limits and asymptotic notations. We will first start by defining functions. We have two arbitrary positive functions, f of n and g of n, meaning both positive functions will be greater than or equal to 0 for all n greater than or equal to 0. We will take the limit from n to infinity of f of n over g of n. In this video, we will only be considering and using f and g functions such that a limit exists. Now we have only these three different outcomes from the limit. Some constant denoted as L that does not equal to 0, infinity, and 0. The reason why there are only three is because these outcomes include all the ways to describe the behavior between positive functions f and g, meaning you cannot find a fourth way to describe the relationship between function f and g. Here is an overview slide of what we have just covered. The limit value has to fall into these three cases. Either limit of f of n over g of n goes to some constant L that does not equal to 0, infinity, or 0. Some of you may already know where I'm going, so how does this tie in with asymptotic notation? When we have a limit that equals some constant that is not 0, it means f and g grow the same asymptotically, which yields us theta. Now here comes the important chart of definition of big O and big omega. These two notations will 100% appear in your homeworks, and you will need to know their definitions. If we were to use big O and big omega, there is a possibility that it falls in this case due to f and g can be equal. If you are not familiar with big O and big omega, and this slide just looks crazy, it is totally fine. We will first look into the other limits and gradually define big O and big omega as we go through each limit. But for what we have just learned about theta, and if a limit that equals some constant that is not 0, we can partially define big O and big omega. We can see that a big O and big omega actually includes a theta notation, and a limit that equals to some constant that is not 0. This is currently an incomplete table. We will fill in more information as we continue with our other limit definitions. Now we will move to the next case. When the limit is infinity for f of n over g of n, we have f grows faster than g asymptotically, which yields us g of n equals small o of f of n. Do note that we have small o and not big O. The meaning between small o and big O is very similar. Small o basically means f strictly grows faster than g. Strictly means if f is n to the power of 2, g cannot be n to the power of 2. G of n can only be, for example, n, log n, or n to the power of 2 over log n. In terms of limit, big O means that it can approach infinity or some constant that is not 0. This also means that the only difference between small o and big O is just f of n can asymptotically equal to g of n in big O notation, and f of n cannot asymptotically equal to g of n in small o notation. So looking back at our previous table, here is our fully defined big O. We are only left with big omega to define. For the last case, when the limit of f of n over g of n is 0, we have g grows faster than f asymptotically, which yields us g of n equals small omega of f of n. Analogous to small omega means g strictly grows faster than f. If f is n to the power of 2, g cannot be n to the power of 2. G of n can only be, for example, n to the power of 2 times log n to the power of 3, or n to the power of 5 over log n. Do note that the possible functions of g are ordered in increasing order. On the other hand, big omega means g grows faster than, or the same as f. This also means that the difference between small omega and big omega is just g of n can asymptotically equal to f of n for big omega, and g of n cannot asymptotically equal to f of n in small omega. Now our table for big O and big omega is complete. To summarize the asymptotic notation, if we have g of n equals to big O of f of n, this means that the limit of f of n over g of n can approach some constant that is not 0 or infinity. In other words, g of n can equal to small o of f of n, or g of n can equal to theta of f of n. Same with big omega. If we have g of n equals to big omega of f of n, this means that the limit of f of n over g of n can approach any constant including 0. In other words, g of n can equal to small omega of f of n, or g of n can equal to theta of f of n. Do not worry about little o and little omega. In the scope of 331, we will focus on big O, big omega, and theta. I strongly encourage you to plug in functions and play around with it to have a better understanding for our examples later. We also have a 331 care package on asymptotic notation. It has a different but equivalent explanation of the asymptotic notations. Here's the QR code available for scanning. And here is an overview of what we have just covered. For each 3 different limit values, here are its corresponding asymptotic notations we can have for positive functions f and g. This is all I have for you in part 1 on 331 background material. If you have any questions, do not hesitate to ask on Piazza or come to our office hours.